Hello everyone, welcome back to a new video. In the last video, we talked about dataset and dataset split. So to get you a very basic idea how learning works, in this video, we'll be talking about three most common types of learning method, which reflects our title of this session, How Does the Machine Actually Learn? We'll start by supervised learning, which is the most popular one, and hope you would enjoy this video. It will be slightly longer. Okay, so supervised learning is where a program is trained on a predefined dataset. So based off its training data, the program can make accurate decisions when given new data. Supervised learning is a machine learning task of learning a function that maps an input to an output based on example input-output pairs. A supervised learning algorithm analyzes the training data and produces an inferred function, which can be used for mapping new examples. In supervised learning, we have labeled training data. As we mentioned before, labels are the answer portion of an observation or the features that we want to predict. So to explain supervised learning, I will give an example. So we can use a training set of human tagged cat, dog labels to train a pet classifier. So keep in mind that this data set, the labels are created by human. So I will use a vivid storytelling way to let you know how this training process is working. So at first, we have a dataset of labeled photos consisting cats and dogs in random sequence. So data are shuffled, and the machine doesn't know anything about the dataset yet. So initially, the model will be initialized to some random parameters. You don't need to know how this way of passing works, but you could just treat it as a process of the machine producing the output. Now we have the data of cat and dog images. We first pass an image of a cat into the model, and the model produces an output saying, okay, is it a dog? I'm not very confident. And you as a supervisor will say, it is not a dog. It is a cat. Please remember that. Okay, then the model updates itself to try to answer better next time. The next time you send another picture of a cat to the model, and the model says, okay, I think this is kind of similar with the last one. I will try to guess, is it a cat? And you say, yes, this is a cat, and please remember that. Okay, then the model updates itself. And then instead of feeding another cat, you will feeding a picture of a dog. The model doesn't know what to do again. It has never seen any dog images. So he says, okay, I don't know about this one. Let me guess. Is it still a cat? Then you say, no, this is not a cat. This is a dog. Please try to remember that. Then the model continues to update itself throughout the process. Now, after maybe thousands or tens of thousands of images feeding to the model is an expert to determine whether a picture is a cat or a dog. Then at that time, when you're feeding a cat image, the model will say, okay, I'm pretty confident this is a cat. And you as a supervisor, you'll still say, yes, this is a cat. And please remember that. So in this process, it's essential that we as a programmers or trainers, we are the supervisor of this machine. We tell it whether its guess is correct or not, or its produced output is correct or not. So if the output is not as expected, we will correct it, and the machine will update itself to learn and in order to make a correct guess. Now there are some types of problems in supervised learning. So mainly are two. One is called classification, the task of predicting a discrete class label. The other is called regression, which is the task of predicting a continuous quantity. So you can see there, the classification is dealing with a discrete class label or categories of data. And regression is dealing with continuous quantity, which are numerical numbers, for example. And in this table we've seen before, right? It's very easy to tell that this gender feature can be a class. So the gender is a discrete class label because there are only a limited number of choices here, like female, male, identified, or something else. It's discrete. But for grades, it must be a numeric number. Although here there's a failed grade and it is not an actual number, we could give it one, for example, like 40. Then we could use this grade as our label in order to do a regression problem, because all of the numbers here are continuous quantity. I do want to point out that sometimes in the data set, the data could not be perfect. For example, here, we would expect all of the data entries to be a number, a numerical one, whether it's a float or an integer. But sometimes like blank data or string text will appear here, and you will need to find your ways to change that part to the ideal data type you're dealing with. Just as a heads up, you will see this a lot in the future if you're doing the training yourself. Okay. So let's take a more close look at the regression problem. The regression problem, to simply put, it is like fitting a polynomial or fitting a function to a data. For example, if we have a Tesla stock price here, and this data is a bit noisy. On the y-axis, we have the stock price. On the x-axis, we have the time. But we could also have the stock price as a function of media exposure instead of the time, because stock price can be the function of time. It could also be a function of media exposure. So they could all be features of each data point. It's just a different representation when we are visualizing it on the 2D plane. Okay, so for example, if I'm dealing with a stock price versus media exposure here, we could have these noisy sample data, which are numbers, and we want to fit a polynomial to it. Okay, so we may fit a polynomial like this or like this, whatever polynomial you want, in order to best represent this kind of data. Then it brings the topic, how do we measure the performance of our fittings? So the best fit we can have is, of course, to let the polynomial pass through all of these points so that it perfectly fits every data point. But what if it does not? How do we measure the fitting performance? There could be an error called mean squared error or MSE loss. For those of you in engineering, MSE could be material science engineering, but here it means mean squared error. How do we calculate that? We're calculating the square of the error in the prediction. So in fact, we're not calculating the straight distance from the actual data point and your fitting polynomial on the same x, but instead we're calculating the area of this square here. So it's a bit larger than what we think at the first glance. And after that, we want to take the mean. So once we have summed all of these areas together, we will take an average and we will get a mean square error. This representation here is specifically what we will use in Python as the sign of exponent. And another thing I want to point out is this mean squared error can also be called MSE loss. Why is it called a loss? It's because we want to minimize the loss and optimize the performance. So this criterion in order to measure the performance is in terms of loss. We want the loss to be as minimum as possible. Okay, so here are some possible fittings. The red lines are the possible fittings of polynomials like 0 degrees, first degree, 3, 9. And the green line, we can see it as the ground truth. So because the data is noisy, it doesn't necessarily stay on this green line, but we can think of this green line as where the actual data, or if there are other data points here, it will lie on this green line. It's in real life how stock price would be. And you could pause for half a minute to think about the performance of these fittings. Which one fits the best? And essentially, I want you to think about two questions. Does the best fit make sense to the model, which is the stock price? And does the best fit model generalize to other data? Now take a minute to think about it.
A few moments later.
Okay, so I think you already have the answer. For the first two graphs, the fitting polynomial is quite simple. It doesn't pass through all of the points, and you can see the deviations are pretty large. So these fittings are not as ideal. And in the fourth case, the last case, if it's a so complicated polynomial through all of the data points, well, it perfectly fits into every data. But is this fitting the best fit in order that the stock price prediction makes sense? Can a stock price versus media exposure be like this? Well, in real life, I think it does not. And because the green line, which represents the ground truth, is lying on this, the data lies on this green line, this fitting doesn't make sense. So in real life, the actual data point could be here, but in the fitting, it's predicting to be here. So this is not a best fit, even if the polynomial passes through every single data point we have. Now, this function seems to have a pretty good fit. It moderately passes through all of the data points, and it's very close to the ground truth. So if we use this model to predict for the stock price with respect to the data exposure, it will be the best fit among these four. So the takeaway here is that choosing the correct degree or types of function can help us better generalize to other data. And the machine learning of regression problems is actually the process to finding the best fit. Now, in classification, it is actually a bit similar to regression, but let's use the same data and we will transfer the regression problem to a classification problem. So for example, we could define that every value above 0 will be good, or it could be a rise in the stock price, and every data point below 0 stock price will be bad, or it's a fall in the stock price. And every data point above this line will be the same. All data points are either good or bad. They don't have any discrete values anymore. These data on the same line, they're indicating whether the stock price is good or bad, right, as our label in classification problem. Now, what I will do is similar to regression problem. How can we use a function to model this kind of behavior? Well, we could still fit a function. For example, you fit a straight line. Every point on this line above 0, we can say it is good. And every point on this line below 0, it could be bad. Or we can fit a function like this, or we could fit it like this, right? So every point on this fitted function above 0, we can say, okay, it is good. And every point below 0, we can say it's bad. This way, we transferred the regression problem to a classification problem. And it helps us solve when labels are actually in discrete class. But in a real classification problem, we usually use 0 and 1 to demonstrate a binary label, for example, true or false, good or bad. And we essentially want our fitted function to represent values between 0 and 1. And it is interesting in Python that true, the Boolean value true, is actually equals to 1 in numerical calculations. So for example, you have a column of true or false, and then you sum them all up, and you are essentially getting the number of truths in this column. This is good to know when you are programming. Okay, then we're officially finished with supervised learning. We'll be moving on to unsupervised learning. Unsupervised learning is where a program, given a data set, can automatically find patterns or structures or relationships in that data set. And unsupervised learning is a machine learning task that draws inferences from data sets consisting of input data without labeled responses. So unlike supervised learning, it doesn't have any labeled responses. The goal of unsupervised learning is to model the underlying structure or distribution in the data in order to learn more about the data. And clustering and association are some of the unsupervised learning subcategories. More advanced unsupervised learning will include, for example, generating new data, like new images, or doing some style transfer. For example, transferring a black and white image to a colored image. So in mid-November, Shubhra, the other mentor, will be talking more with unsupervised learning and a specific algorithm called k-means clustering. So to help you understand unsupervised learning better, there are a few examples. So for example, analyzing a data set of emails and automatically grouping related emails by topic with no prior knowledge or training, which is also known as the practice of clustering. It is an example of unsupervised learning. So in this process, the model could automatically group related emails into a cluster. So when you see the final result, you can see that which emails are grouped together and it is easy for you to put a category on these emails. And from my own experience, I've done depression early warning research last summer with CAMH. So at that time, we have a tremendous amount of patient daily behavior and their self-survey data. And we want to cluster those patients into groups in order to study their behavior and the relationship with their depression level. And at the end, we study the trajectory of patient group, which is the patient's movement between each group in order to infer more about a possible relapse. So the intuition of unsupervised learning is that we are no longer supervising anything. We do not provide the label for any data. The machine will find out something itself and tell us the result. The advantage is that the machine can find out something human beings cannot observe from higher dimension of data. So here's a more concrete example of clustering. On the left, we have unclustered data. They do not have any labels. And keep in mind that even if you see x1 and x2 here, there can be multiple features. So we can only visualize it on 2D, but the data itself is actually on higher dimension. And on the right, we have 3 groups of clustered data by the unsupervised learning model. And as you can see, it automatically groups the data into 3 groups. And there are another concept called centroid in the unsupervised learning algorithm. So a clustering algorithm can be learning to find a certain number of centroids so that the distance between each data point to the nearest centroids is minimized. So for example, if the centroids are here, then the clustering will be the best in sense. But if we, for example, have the centroids, 2 centroids out there, very far away from this major group of data, then this cluster will be actually very small, and this cluster will be very small, and all these data will probably belong to this centroid. Then this grouping doesn't make much sense. So, and when we're talking about the distance metric can be different. So in real life, in 2D or 3D space, if we're talking about straight distance, we're actually talking about the Euclidean distance, where we use Pythagoras theorem to find the distance between 2 points. Or we can calculate distance in some other ways to use higher order functions. We will be using different distance metric in our tutorial in this session. So that is all for unsupervised learning. And finally, we're moving on to reinforcement learning. So reinforcement learning is the purpose to train a model in order to maximize the reward via iterative trial and error. And it is learning what actions to take to optimize long-term reward. So in this graph here, we have an agent which contains the model in reinforcement learning, and the agent is able to produce an action into the environment representing the action the agent wants to take. And the environment will give 2 data here. One is called state, which represents the state of the agent inside the environment, and also reward. Now, this reward is very interesting because the goal of this agent is to maximize or optimize its reward, so to represent a better performance. So the examples of reinforcement learning could be achieve a complicated task with non-trivial control. Nowadays, many researchers are learning to use reinforcement learning to, for example, play a video games, do some simulation, and it's massively used in robotics because for robotics control, the environment is very complicated, and often we're dealing with very complex control methods. Usually, you don't have a straightforward control. Instead, you may have a discrete or a continuous action space, we call it. So in this way, supervised or unsupervised learning cannot better manipulate this robot or in general the agent to complete a very complex task. So we will use this reward to train this agent to achieve its task. And here are some examples. I think many of them are very famous. For example, this AlphaGo that we talked about in last session. It's using reinforcement learning to train its model, and it actually beats an actual human player. And we will be publishing an article about a more advanced algorithm of AlphaGo, which is called AlphaZero, in a few days. And other reinforcement learning algorithms could be, we could use reinforcement learning to train the agent, which is this Flappy Bird, to play the game. And think about the reward. Reward could be just this score, right? We want to maximize this score in the long term so as to train this Flappy Bird. So it's a perfect representation of using reinforcement learning. We could also train reinforcement learning agents to play these kind of simple games, which is not very complicated in the environment and the control. And as I demonstrated another video last session, which is the reinforcement learning cars, the distance travel is actually the reward of this car. The car wants to drive along this road in order to get as far as possible. And for more state-of-the-art or complicated training, it could be reinforcement learning on the Warcraft or StarCraft player or agents. So this would include a more complicated environment states and its control methods. And actually today, when I was driving on the road, I encountered a road bump or so-called speed bump. I was thinking why people design this way for drivers to slow down their speeds. Well, ideally, we should not drive at high speed to pass the speed bump. But what if we don't know the effect of speed bump? For example, when I was first driving, I don't know how this bump will do to my car, so I just drive at a very high speed, and the whole car nearly flies. So it was pretty scary to drive at high speed. Then I updated my method to drive through. I use a lower speed, but the car is still bumped up, and it doesn't feel good. Then I keep adjusting my behaviors in driving. Finally, I'm being very careful and driving at a very slow speed in order to pass this speed bump. Then it's pretty comfortable. So in this whole process, I'm, as a human being, and was updating my own behavior. It's very similar to reinforcement learning. Right? Every time my car and myself was bumped up, I receive a very low reward or even a negative reward because I don't feel happy about it. I'm scared. So I want to adjust my model, my brain, in order to best fit this environment and get a good reward, which means to pass through the speed bump at a comfortable state. Yeah, so reinforcement learning is very interested, in my opinion. Okay, then congratulations, and I really appreciate that you have made this far to this session. It was pretty long, and particularly in this video, we've seen 3 types of major learning algorithms in machine learning. So after this video, you will get a very clear sense how people, researchers, engineers are using machine learning to achieve some of complicated tasks in our real world. Okay, hope you enjoyed it. Thank you for watching.